So yeah, so this now that we have the overview done, we will now transition into these actual hands-on exercises that we have prepared, and these are all about the NOMAD Encyclopedia. So first of all, I'm just gonna quickly introduce myself. So my name is Lauri Himanen. I'm a part of the NOMAD software development team. Been working for quite a while already with both the NOMAD repository, which is all about these individual entries and data sets and uploads, and then also with the NOMAD Encyclopedia, which is now more about materials and how you can find materials within the NOMAD infrastructure. So let's just start out with a brief overview. So the agenda is such that I'm gonna first give you an overview of firstly the motivation behind the NOMAD Encyclopedia, what kind of solutions it offers, and how it integrates with the other NOMAD services. After this fairly brief overview, we're going to transition into the actual exercises, and these are split into two different sections. So first of all, we're just going to take a look at the graphical user interface of the encyclopedia, where we will just demonstrate the basic functionalities that you can do through the GUI. And then we have another set of exercises which are related to the API. So we also provide this REST API for accessing the data programmatically. So there's going to be a few exercises regarding that as well. And all of these exercises are such that I'm going to walk you through them. You can then directly live do them yourself as well. But then we will later also post, or the slides are already available, and then we're going to post also the exercise solutions as well later. So don't really be too stressed out if you don't complete them here. You can take a look at them later. And also tomorrow we will have the Q&A sessions where you have plenty of time to ask more questions related to these exercises. At the very end, if we have some time, I'm going to discuss a few things about what the future looks like for the encyclopedia. So there we have a couple of topics that I'm really excited to talk about. So let's just start out with the overview. And as Christoph already mentioned, there's plenty of these materials databases, encyclopedias, whatever term you want to use out there. And this talk is all about the NOMAD version of these. And we, if you go to basically the project front page, we immediately on the front page offer you two ways of exploring the data. So you can either go for the calculations or then the materials. And then this talk is all about the materials side of this exploration, and how do these two things now differ? So we have basically two kind of services. We have the repository, which is organized in terms of what people have uploaded, what kinds of data sets they have created, and what sort of entries are within these uploads and data sets. And basically, as a user, you upload your raw data, from which we automatically detect these individual entries. And then you can yourself define grouping for your data. So you can generate these data sets and even assign DOIs for your data sets. And then this way, other users can basically then search these individual entries and data sets based on whatever the method, for example, the properties that were calculated, or the chemistry that is basically present in these entries. But often this kind of basically aggregation to these data sets and entries is not so useful always, because often materials research is really about specific materials. So you really want to find or kind of aggregate these entries using these materials instead. So a material, what I mean by material is that it could be a well-defined crystal structure, for example, a two-dimensional material or a polymer, and you want to sort of somehow group all of this data in terms of these materials. And this is really then the goal of the NOMAD Encyclopedia. So we organize and provide access to our data in terms of these materials, and basically the entries that are related to these materials. And the hard part about this is that there's no explicit connection between the materials and the entries. So Christoph already mentioned a few of these other databases like AFLO and OQMD and Materials Project, where the situation is slightly different, because often they start out with some material class, for example. For OQMD, I think it's currently always bulk materials. So they basically know the connection between a material and the individual calculations. For us, NOMAD is quite unique in this sense that we do not really restrict what kind of data users can upload. So all of our data comes from a very large pool of users, and we have no control, and neither do we want to control how they really build their entries and what sort of materials they want to investigate, what sort of properties they want to calculate. So we are kind of we have the basically this unique opportunity of gathering a lot of heterogeneous data, but alongside with this comes this problem that we don't have an explicit connection between the materials and the entries, because there is typically there's no way to let's say programs which you, for example, use to calculate some theoretical data, they don't explicitly contain what material was really contained in an entry. And so just to reiterate what I mean by these materials is that, so basically in order to automatically detect these materials, we need to have some sort of a quite strict definition of what a material is. And for us, this means that our materials really need to have a somewhat unique structure, and this structure is used to identify it. And of course, there needs to be some tolerance towards scaling and noise in these atomic positions. And some of these examples that would fit this kind of category would be, for example, polymers and 2D materials, bulk systems with periodic unit cells. And these are the kind of what you could call building blocks that really allow you to also then build more complex materials. But this is what I mean really by materials. And this is also because we use this kind of a structural information to really detect the material. It also means that the original data needs to have some structural information for us to basically be able to detect these. And then I'm just going to quickly mention these two ways we use to basically build these links from entry and its structure into a material. So as I said, we use two different identification schemes. So I'm just going to talk about the topmost first. So this is based on the symmetry properties of the unit cell. So we extract the space group, extract the conventional cell, the set of Wyckoff positions within the cell. And we use this information to create essentially a hash that then identifies the material. But this approach is only suitable for these systems where first of all, we have to have the unit cell, and it needs to also have a fairly fixed symmetry. This, and basically because we use the symmetry properties to create this material ID, it is also robust against scaling, for example. The symmetry properties don't change if you scale the system. And also there's like built-in robustness towards like small noise in the data, because you almost never have perfect symmetry in these kind of calculations, for example. So there is like a tolerance there as well. And now that these systems that then do not really exhibit this kind of degree of symmetry have to use something else. And here we come to the second option, which is this kind of a descriptor-based method for building the material links. And here and this is basically utilized, for example, for 1D systems, and which basically don't have any more enough symmetry for the symmetry-based method to work. So the idea here is that we start out with the structure, we take out the primitive cell out of it, and then what we do next is that we build a so-called descriptor, which is basically it's just a numerical vector. It's a vector of numbers, fixed-sized one, which to some degree encodes the structural properties and then also the chemistry of your structure. And you can take a look at the references for more information about how you would go about building such a descriptor. There's a plethora of tools available for doing this. But what you'll end up is that you'll end up with a numerical vector that is then also invariant to rotations in the structure or translations. And then this kind of a descriptor you can then also discretize. So what you'll end up with this is you are basically mapping these structures into this descriptor space, and you have these discrete locations in this space from which you can once again through a hash function create these material IDs. So these are the two kind of methods. Both of them basically start out with some structure, and you end up with a fixed size hash that becomes our material ID. And this is essentially the system that we use to build these links. So from an entry that contains a structure, we can create a material ID, which then means that this entry is associated with this and this material. This is the overall process. And now the encyclopedia is all about now using these materials and the material IDs to serve information about the data that we have in NOMAD for the users. And we have two services. We have the graphical user interface that allows you to apply different filters and select from a list of results and browse the information for these materials. And for each material, we provide 4 different categories. So there's the structure category, methodology, electronic structure, and vibrational and thermal properties. And we're going to very soon go into the exercises and take a look at the GUI in more detail. And then we also have this API service where you can actually do more programmatic queries. And we're going to have the second set of exercises is all about using this API to access the information. But I think we can actually go on to the exercises just to give you maybe like an idea about how the platform itself looks like. Then we can maybe have a few questions if there are any, and then we'll go later on to the API exercises. So for this to work, I'm just gonna go into a slightly different view. So we'll have here page open, and if you want to follow these yourself and try out the GUI while I'm speaking, you can find the slides for my talk in the tutorial web page, and inside the slides there's also all these links that we will be using. So let's just have this side by side here for now. So let's start out with the GUI exercises. So here we have our page. Let's resize this a bit. And the first exercise is really about just doing quite simple, basic queries about materials inside the encyclopedia. And the first task is about find the average GGA lattice constant for gallium nitride in the board side structure. And then also we're going to do the same for this iron BCC structure. But let's start out with the gallium nitride, basically. So what you would do here, it's a fairly typical search interface where you have the periodic table. So let's start out by first selecting just our elements that we want. Let's apply this. And in here, we can also toggle if we want to allow other elements. So not just gallium and nitrogen, but also other ones. In this case, we don't actually want anything else. So let's enable this as well. If we want to, now you can see that we still have quite a lot of, so all of these are individual materials that we have. And there's quite many still here. So we're going to restrict the search even more. So we wanted to look for word-side. So let's type it in here in order to activate this filter. And now we have actually restricted the search so much that we end up with the actual structure that we are looking for. And this, once you click and select an entry here, you'll come to this kind of an overview page for the material where you have these different sections that I mentioned. So we have the structure, electronic structure, and methodology. And if there's also the vibrational properties, they'll be here. And now, because the exercise told us to basically go for the lattice constants, so we're going to find them in the structure. So let's go on here. This will open like a more detailed view about the structure. And here we actually have some statistics about the lattice constants. And these are really aggregated from all the entries in NOMAD that are associated with this material. So we have, for example, the mean lattice constants for these three different lattice vectors here. You can also select basically the methodology. So for GGA, it looks like this. For hybrid GGA, it looks like that. And for GW, it looks like this. And we can also see the distribution of these different lattice constants in this kind of a histogram, if you wish. So basically from here, we can, like the exercise told us, we can see the average GJ lattice constants for this structure are these. So A is this, B is this, and C is this. Now we can do the same thing for this iron structure. So let's go back again to our periodic table. Let's disable some of these filters here. If we select iron from here, and then we start out also, once again, no other elements. And the question was about a BCC structure. So let's type that in here as well. And this will restrict ourselves, basically this material that we are looking for. Let's click it when we can do the same thing here. It's going to load us this new view. And once again, in the structure panel, we can see these lattice constant that we were interested in a similar fashion. And you can see that these distributions can be quite broad, because now, of course, there's plenty of different entries for this material, which have not used the same optimization and not exactly the same methodology. It might be GGA, but something else might be a bit different. So there's going to be a distribution. So this, you also have to be careful as a user to take a look at these distributions. You can find some outliers. You can take means to kind of get some more robust information. And basically here you have the solutions for this exercise. So we found out that the structure had these and these lattice constants, and if you compare them to the experimental ones, they're not too far off, at least according to this source. So with these means are actually quite close to the experimental values for GGA. Same for this iron structure. We are very close there in these lattice constants. So that's basically how the very basic searches work within the encyclopedia. So you can click through the periodic table, search a few, for example, the structure type and so on. And the second exercise is then about formulating a bit more complicated query, where we are actually using logical operators to restrict the search. So the question is that we want to query for a material that contains only gallium and then nitrogen or phosphorus or AS, basically. So we will need to use these logical operators to form this query. And I'm just gonna give you an example of how this look like. So let's once again clear up our previous search. So what you would need to perform these kind of queries is you use this logical combination toolbox here. So we're going to start out the gallium here, but then we are going to start using these logical combinations. So we will be using the AND. So this is basically a switch where you can switch between and or. So the first is that we want gallium and then we can say nitrogen. Now we're going to switch to or, because the query is about or, then phosphorus, or the AS here. So in this way, we can produce this kind of arbitrarily complicated Boolean operators between elements. And once again, we don't want other elements. So let's hit the search. And from here, you can now see that you'll end up with materials that, as we asked, contain gallium, and then it's either arsenic or phosphorus, or then there's also maybe an example with nitrogen here as well. For example, here we have also the gallium nitride here. So this would be the way you would compose this kind of more complex logical queries for elements, and this works for elements, and you can also combine formulas with these logical operators, and can become quite complicated as well, these queries using this syntax. So now that we know a bit more about these more advanced queries, there's the solution as well, but let's go to exercise C. So now it becomes a bit more interesting, where we try to find 4 different carbon allotropes. So these kind of quite basic things that we might expect to find in such a materials database. So we want diamond, we want graphite, the alpha version, graphene, and then some kind of a nanotube. So basically we have 4 different allotropes that we want to try and search for. So let's start out. First, I think the simplest one is going to be diamond. So let's go for the element that we want. So only carbon, and we have a total of 65 different materials. Some are very exotic. So if we want to really narrow down the search, we will need to once again specify the structure type. And once we go for diamond, we can see immediately what we are looking for. So this is the first allotrope. So that was fairly easy. What would be a bit more difficult is the graphite. So now once again, let's go for carbon only. And now we have to know, because there's no really a structure type for graphite, so we need to know the space group. Luckily, we do know it for the alpha graphite. There's still, even if we specify the space group, there's going to be quite a few examples here. We can take a look at a few of them. So there can be quite complicated ones that still have the same space group, but are not quite graphite yet. What is often useful is to take a look at the number of calculations associated with the material. So typically the ones that have lots of entries are the most useful ones also. So let's take a look at this one, which has almost 200 calculations associated with it. And this is now starting to look more like what we want. So this is the alpha graphite that we were exactly looking for. You can see more of these structural properties to really verify that this is what you are after. So you have the structure designation here and the Wyckoff sites, and more of these symmetry properties here. So that's graphite basically. And let's now go back to the third one. So the third item that we wanted to use was graphene then. So basically a single graphite layer. And luckily for this, it's going to be quite easy. Let's keep the carbon here. So now you can also specify the system type. So we have bulk 2D and 1D. So we know that graphene should be 2D. Once again, we have a few examples here. We can, for example, probably know that it's going to be this, but let's take a look at one of the less calculated ones. For example, here we have something that is almost graphene, but not quite. You can see that the lattice is distorted by somewhat, and this is also one of the challenges that I want to point out with this material identification, where essentially there's a point where you have somehow distorted your system just enough that it no longer falls into this, what we would say, what is graphene in our database. So you just gone above the threshold, and then it becomes a new material. And this is quite tricky to kind of know where these boundaries lie. So we have some set of default like tolerances that we use, but it's really tricky to know which are kind of good, sensible tolerances. For example, is this graphene or not? It's kind of debatable. But if we want to look at what kind of the expected graphene looks like, it's more like this, where we have like more perfect hexagonal symmetry here. And this is basically the 2D structure that we are now looking for. And let's take a look at the last example. So a nanotube. Once again, we're going to use the system type filter here. So instead of 2D, we know that nanotubes should be 1D. So we have a few examples of these carbon 1D structures, and I think all of these are this kind of nanotubes we can take. For example, the first one, we can see that this is once again, it's a repeating structure in this direction. And we can see it's this kind of a tube that basically forms out of there. So we found our nanotube here. There are, I think, bigger ones as well. So this is a bit larger one that somebody has calculated, and so on. And there's a few, only one or two associated. So these are not very popular currently in our database. And basically, this hopefully kind of illustrates how you would go about and finding these kind of interesting materials that you are after. So you really kind of also have to know a bit which filters to apply, but typically you can quite easily find what you're after by applying a few filters here and there. Let's take a look at the exercise D. So this is about finding the specific heat of platinum at room temperature. So this would be maybe a more realistic case where somebody is really interested in a physical property of a certain material. So let's try to formulate this query, and let's go back to the table of elements. So we were talking about platinum, and we know that in room temperature platinum is going to be in FCC structure. So let's apply this. And we have already filtered down our results to what we are looking for. And in here, you can now see an example of the vibrational and thermal properties as well. So for this particular material, there's also an entry that contains the specific heat. And at room temperature, we're going to be around 125 or so in here. And you can also really go into more details and check different calculations and what sort of properties come from different calculations. So this tree view really gives you like this hierarchical view to these individual entries that have calculated a certain property for this material. There's a few examples of this here. And if we take a look at the experimental value, we can actually see that, for example, the experimental specific heat is around 133 joules per Kelvin per kilogram. So this 125 is not that far off. So the theoretical result is quite well in this case. Let's take a look at the final GUI example before a few questions that you might have. Then we go into the API exercises, but let's first take a look at the last one. So this is about finding a material in rock salt structure with a GGA band cap over 5 electron volts. So this is once again towards more and more realistic cases. So let's see. First of all, we were interested in rock salt structure. So let's enable this filter. We wanted the band cap to be at least 5 electron volts. Let's apply this. And what else? And we want GGA. So let's select the functional type from here. So now we are pretty much set. What is important here is that we will want to enable this what we call restricted search. So let's click on this button as well. And what this basically does is that it is gonna essentially inside our query, it's gonna combine our query about the band cap and the methodology. So now we are really targeting a material which has a single calculation with a band cap, a GGA band cap of this value. If we disable this, what we are essentially searching for is, once again, materials that there's a calculation with a band cap of 5 and then there is calculations with a GGA function, but they don't have to be the same calculation. So because each material has several entries that are associated with it. So essentially there can be one entry that has a LDA band gap and some GGA calculation. But this is typically not what we want if we are, it can be, and that's why we have the option where you can really restrict it so that these two are combined, so that we know that a single calculation with a GGA band gap of this is quite useful for this kind of queries. And if we take a look at this material, we basically found what we wanted. So this is the material that has a GGA band gap over 5 eV inside the NOMAD Encyclopedia. So that basically covers the GUI exercises, and I think this would be a good point for some basic questions about the encyclopedia in general, about the GUI, before we go more into the API exercises. So I think I'm just gonna stop sharing for a while, and I can take some questions from you now if you have any. You can either post them in the chat or raise your hand if you have now any further questions just related to the overall what I talked about, how we actually connect the materials and the entries, or how the GUI works, or how we do formulate this and that query. If there's no particular questions, okay, there's at least one in the chat. So there's a question about, is there a way to enter the composition just with a keyboard? So currently not. So the encyclopedia GUI is really kind of heavily mouse oriented. So you really have to click. And also the search bar is kind of just shows you the current search. You cannot really type anything in there. And this is going to be like one of the points that I will talk at the very end. So we are currently bringing the NOMAD repository and the encyclopedia together more and more, and hopefully we will be able to have a more common search interface between these two services, where we will also kind of have these kind of dynamic search bars and so on. But for now, if you want to do something more programmatic with the encyclopedia, you typically want to go for the API. So there you can do quite a lot of automation and more complex things. So the current GUI is kind of very mouse oriented, I would say. And we have any other? So there's Pepe, for example. You can just.
Hello, Lauri.
Hi.
I don't know if my sound is good. I just wanted, so right now the materials classification is basically based on the structure, but when we like try to also like introduce experiments in here, I mean, all the experiments that we would really know the structure very well is like crystallographic experiments where like people refine the structure and know this like very well. But this is like a very small fraction of what we want to cope. How would you envision that we could like group materials, like only based on the composition?
So there's a very good point that basically we are now, the encyclopedia is almost exclusively about theoretical data, where you have this structure from which you can go for a material ID, and then you have all of these connections. Now with experimental data, I would say that it becomes more a responsibility of the researcher to somehow bring this information in. And what I could envision is that it could be as simple as, when you upload some experiment, you could, if you know, for example, you go to the encyclopedia and find this material ID, you just put that in there in your input, in your raw data somewhere in the archive. And this would allow us to link now experiments once again for the encyclopedia and their results from these experiments to the encyclopedia. But this is now something that to some degree requires more from the researchers, some more effort and more knowledge. And then there's also, of course, this uncertainty. So in theory, you don't have this because you always know what system you are looking at. But of course, in experiments, it becomes a bit of a question: can you assign a material ID if you're not sure about the structure completely? So then really it becomes a much more difficult problem, and I don't have a very good answer. If you are really uncertain about the structure, then also we cannot provide this link. But I think for this kind of, for example, if you're measuring the crystallographic properties of a bulk sample, I think it would be fairly okay if you let the user to introduce this data manually in for us to create these links. So that, I think that would be the way to go.
Thank you.
If we have no further questions at this point, we can also have more questions at the very end. I would just go to the API exercises that I've prepared, and just okay, I'm just going to share my screen once again. This here as well. So now we're gonna transition into the API exercises, and in here, if you wanna follow these live and do them really as I speak, what I would encourage you to do is to just open a new notebook. I would recommend using Colab, for example, because I tested this, and basically everything works by default. All the libraries that we need are going to be installed here. So you can just go to Colab and boot up a new notebook there, and whatever I type on the screen, you can type in here, and it should work here as well. So it already has all the libraries installed that we gonna need for these exercises. So this is a very quick and easy way for you to start doing things yourself as I speak. Of course, if you have already your some sort of a Python environment ready on your local machine, you can use that as well. So, but basically the idea is here that I'm just gonna guide you through a few interesting API exercises that show you how you would use our API to access the encyclopedia information. And I'm going to use Python, but in principle, the REST API works with any programming language. Python is just very convenient for this kind of work. But you could use any programming language, and you can go and look more about what our API offers at this link. So there is, for example, there's actually underneath this link, you can find a bit more about how you use the API. So there's a bit of documentation, basic documentation about how you get started. But then there's also the actual API endpoint documentation, where you can see all the endpoints that we offer and what sort of information you're supposed to put in and what you will get out. So this is also very useful if you want to dig deeper and see what you can do with the encyclopedia. But let's now start with some basic exercises. I'm just gonna type them here as we go. These are not so large, and as I said, we're gonna post the solutions online at the tutorial website later, so you can also then find them there. So let's go back to my environment here. I'm just gonna make the font size a bit bigger So the first exercise is really about using the encyclopedias / material ID calculations API path to gather all the calculations that are available for the sodium chloride in rock salt structure. So we for this we need to have the material ID, which we can get just through the GUI, or if we know it's through some other means, we have it already here. And now we can use this ID. So inside here, I've stored it inside this variable, and we can use this to basically construct our query. So what we're going to use is we're going to use this requests library that is all about performing HTTP calls to a server. So we will know that we have this endpoint that serves this information. We can also take a look at it in here. So we're going to use this endpoint. So, and this is used to return information about all calculations related to a given material. So this is exactly what we want. So we're going to use this one. And we have the URL here. We're going to go for materials. Then we have the material ID here. It was NEC ID. And then we will use the calculations. So this is going to be our request. Let's just make it into a JSON. What we're going to do is let's just print out some of the results within here. So we can take, for example, the first calculation, and let's take the identifier from here. Now we can actually also run it here. So let's see. Just gonna run it through here. So let's take a look at. Okay, we're missing one from here. So we're still missing one thing from here. Yeah, we're missing the actual method. So we want to use the get method. And this is also, you can see, again, one thing is calculate. Let's make this into calculations. And what I'm just going to show you. Shall be fine. Let me just copy from here. See. Okay, now we got it running. So basically what we are printing out is now the calculation ID of the first calculation associated with this material. I'm just going to open up the API endpoint here so that you can see that we have essentially used this materials entry or endpoint. We've given it the material ID, then the calculations, and the response is going to be something like this. We've accessed the results, which is a list here, list of all the calculations, and we've taken the calculation ID of the first result that we get. And now the question was about then also using this calculation ID to really look for this entry also in the repository. So we can this way kind of have a link between this what we find in the encyclopedia to also what is contained in the repository. So let's just copy this calculation ID, and let's put it inside search here. So in here, it's going to be called entry ID. And if we perform this query, so this is now the NOMAD repository that is all about the entries. And now we can find this particular entry that we found related to this material. So we can also verify that we have exactly what we wanted. So this is some calculation for exactly sodium chloride in this rock salt structure, and it has actually quite a few properties calculated within it. So this a very basic illustration of how you could use the API to query a few things, properties, and also how you can like relate the repository and what you find in the end. So let's go on to the next exercise, which gets a bit more complicated. So now we're going to use the materials API path to query all 2D materials and get the material IDs of 3 materials with most calculations performed on them. And then we can check the findings in the GUI. So let's start with this. Let me just disable this for now. And now we are gonna use this materials endpoint, and we're gonna essentially, here you can now post those filters that we also used in our GUI example. So you can really specify the formulas and structure type and so on inside here, and you will get essentially this, what we saw in the GUI, this list of results from where you can also pick the different things up. So this is something where you can really use programmatically to construct these kind of queries that I showed using the GUI. So let's just form the call, and we can see that now we're going to use the post method. So in the documentation, you can see in these green and blue labels which method you are supposed to use. So in the get method, we basically don't input any body into the query, but in a post query, we can really give, for example, a JSON body that can then be used to construct a query. So we're going to use the post one. Let's just start out. So first of all, we're going to start out once again with the URL. Now it's materials only. So this is going to be our path. And now we are giving it some request body. So we will want to use this kind of a pagination. So we want 200 items per page. And here we have our query. We wanted 2D materials here. So let's say it explicitly here. So yeah, we're doing a post request to this path, and we have this kind of a payload. So we want 200 items. We want the material type to be 2D. And let's also fix this here. And let's see what we get out. So we're going to take transform this into JSON, and let's print out something from this. Once again, we have a response object. So let's print out what was the total amount of results here. So this total gives you the amount of results that we got with this query. So we asked for 200. Let's see how many we got actually. And now what we wanted was that we wanted these, was it top 3, I think? Query all then as the top 3 materials with most calculations performed on them. So what we will want to do here afterwards is that we're going to sort this list of results basically by the number of calculations, and let's take the top 3, and we're just going to print out the material ID for these, and then let's check in the GUI what these top 3 actually were. So we go into the results. This is the list that we are now sorting. Let's sort by, there's a field called number of calculations. We're gonna just reverse it so that we get the top ones. So this should get us that far. And let's just take the top 3 from here and print out their material IDs. So with this, so we to reiterate, so we got all 2D materials. We're going to sort them by the number of calculations, and then we're going to print out the top 3 with the most calculations. So let's see, and then with these material IDs, we can also take a look in the GUI what they actually look like. Let's see if this goes to fine. We have at least one error. This should be pages. So here we see our results. So first of all, we asked for 200. There's not that many 2D materials yet. So there's only 165. So at least we know that we got all of them. And now we have the top 3 material IDs. So let's just use these to really check does our query make sense to some degree. So we're just gonna type these in here in our URL and then just check what kind of materials these were. So the first topmost one seems to be this, I think it's boron nitride. So this requires quite a lot of calculations in here. You can see in this methodology that there's from different codes quite a lot of calculations for this material. So that at least verifies that we made some sort of a sensible query. Let's see the second one. And this would be also something we would expect. So now we have the graphene here as well. And just to illustrate also one other thing, we're going to take a look at that third example, which is going to be a bit, maybe not so traditional. So here we actually have a 2D material which consists of 2 layers. And this is something I'm going to talk about a bit later in my tutorial. So we also have these kind of systems that are constructed of what we would say multiple materials. And currently it's quite, our analysis is not as intelligent as to separate these two materials together. So they are seen as one large material, whereas a researcher would really see that this is material A stacked with material B. This is something I'm going to come back to a bit later, but I just wanted to let you know that this is something that can happen, and that we are trying to build a new system to kind of take this more into account. But this is really something that also can be a bit blurred, this line where is it a single material or is it two materials? So this is a very tricky topic as well, but I'll come back to this a bit later. So with this, I think we are done with the exercise B. And what we can now go for is number C. So we are now interested in using this groups path to gather the list of available equation of state calculations for silicon in a diamond lattice. For one of the groups, we'll use this group API to gather the energies and volumes and plot them in basically a 2D plot. So what we're interested in, we want to plot this equation of state for one of these materials, essentially. So first of all, let's take a look at what the documentation says about these endpoints. So we have the groups endpoint, and it returns a summary of the calculation groups that were identified for this material. And these groups are basically some form of set of calculations that form a result that is gathered from several individual calculations. In the case of equation of state, you have calculate this material with different volumes, and then they each have their own energy. And with this, you can plot this kind of an equation of state. So we also do this kind of grouping in the encyclopedia, where we actually can, to some degree, know how some of the entries are grouped to produce a result for a single material. So let's start out with this this task. So we're first going to use these groups to return groups for this material that we're interested in, and then take one of them and basically plot it. Let's start out here. And I think we can just, for now, this note and start our new request here. So we first want to get these groups. Now we can use the get method. And we already have the ID that we were interested in. So we have the material ID for silicon diamond lattice here. We're going to just insert it here. And now we go for the groups. Let's make it into JSON. And so this should return us all the groups for this material. What we're going to look for is that we want the equation of state group from here. So let's take these. We know from the documentation that it should have this group's EOS key here. EOS stands for equation of state. We're going to take all of these keys, and let's take the first one. We're just going to take the first equation of state group here. And what we can then do is we're gonna now that we know this this group, basically we know this is an identifier for it. So now we can use this other endpoint that actually, once you know the group ID, you can use this endpoint to get the whole set of data. So in this case, it's going to be a list of energies and a list of volumes. So let's take these out here. Once again, we go for this kind of a path, slight modification. We know that we want the EOS, and let's put in the ID here that we have just resolved. And this way we get the group information. And now we can, so we wanted to produce energy versus volume plot here. So let's take the energies from here. We're just going to make them into a NumPy array. We know that it contains them in here. We're going to do the same for volumes. This should basically give us all the information. What we're going to additionally do is that we're going to sort them from lowest volume to highest volume so that we get a nice plot. So I'm just going to get the sorting for these volumes. In here, so this should give me the indices that sort these things out. And now I'm just gonna plot it out. So what we want is we want to sort first volumes on the x-axis, but we want to use this sorting. So the smallest point first, largest next, and we have to apply the same sorting for the energies in order to get a sensible plot. Something like this. And let's see what we get out, and how many typos we have here. I think this is too much. Okay, now it looks better. Okay, let's see what we get out of here. This runs fine. Do I still have a typo here? No, it actually ran just fine. So now you can see that we successfully got one of these equations of state out of the encyclopedia. So we got the raw data, and we were able to do whatever we wanted with it. In this case, we just plotted it out. And this was for silicon in a diamond structure, which is this material ID. So this is a bit more advanced case where we were using this grouping that the encyclopedia also offers for a material, where we can have these groups for equation of states, and there's also one for the parameter variation and so on. So, and you can take a look at the documentation to see a bit more. I think this is quite useful for finding this kind of information for a specific material. Because, for example, this kind of information is not something that you can currently find in the repository. because we don't have these groups available there. And I think this brings us to our last example. Yeah, okay. So in this last example, we are interested in plotting the representative density of states of sodium chloride, once again in the rock salt structure, together with the density of states of one of the similar materials. And this is also another feature that we have in the encyclopedia, particularly for DOS. So we have a kind of a similarity measure between DOS values, and we provide for each material which has a DOS, we provide the list of similar materials in terms of the DOS values. So we have this endpoint. Basically, each material provides these similarities inside this endpoint. So once you have your material ID, you can basically make this call here, and you will get out also a list of similarities, and this is in terms of DOS similarity. So we will know that this material will have or linked to other materials through this DOS similarity. So this is something we can use to find a material that has a similar DOS, and we're gonna just plot two of these DOSes out to see that, for example, does the similarity really match? Are those DOS values similar? So this is the point, and I think we will just start out doing this final exercise. And for this, as mentioned, we're gonna first use the materials path here. So let's just take this template here. So think we can. Okay, so let's first take these calculations here. We have the URL materials. We want the NAC. Oh yeah, exactly. We will want the representative one. So this is what we show on the overview page. And this is under this key. So again, we can check it then through here. It's actually under here. So the representative ones, and we're gonna look for the representative electronic DOS. Like this. And now we can make another post request where we actually get the actual DOS value. So now we only got the IDs, the calculation IDs for this representative DOS. Now we really get the actual data through another other call. So once again, it's gonna be materials. We have the NAC ID here. Now we want to go for the calculations, and we have the NaCl DOS ID, which should have been assigned here. which we're going to put in here. Okay, great. And now we are this far. And we can specify here in the payload which properties we are interested in. In this case, we don't want to get everything. So we're going to specify that we only want the electronic DOS. Okay. Great. So now we should have the DOS values for the representative one. And let's just try, and we can plot them directly here. So we have already the sodium chloride density of states here. And once again, you can look at in the API documentation what these exact keys will be. Will be DOS values in this sense for the x-axis, and then it will be DOS energies for the y-axis. Okay. So now we have this part covered. So what we've done here is that we were just plotting the representative DOS for NaCl. Now we want to find this similar DOS, and this we will do by getting this this similarity information through the API first. So we're gonna go for this kind of a route where we don't get calculus, we get actually the material information. Make it in JSON. We want to extract the ID, so the actual material ID for the similar material. Let's take the first one. This is the most similar one. And then let's take we want the material ID out of it. So this is going to be the calculation or the material that is most similar. And once again, we can do the same kind of deal. We get the representative DOS for this material, and we then plot these together. So we can actually just gonna copy paste it here because it's not so interesting to get it. It's the same kind of code here that we used to get the representative for the NaCl. So now we have we're gonna just use a similar ID to get the actual calculation, get the representative one, and then plot them once again together. So the similar DOS now together, and here we are basically just gonna limit these plots to a certain range so that we can focus on this range from -5 eV to 10 eV. And I think we are almost ready to run it once we fix a few typos here. Let's see. Not because we still have this running. Let's close this one. see if we have other issues here before running it. Let me see. Can I see all those? So we still want to make this into a JSON document, and just type it in. And now we really want the electronic dots out of here. Okay. Once again, the same. This looks correct. Let's see what we get out of this. There's still maybe something wrong. Yeah. So same type of here. Maybe one more thing before we get it running. Then we're missing the method we want to use here, which is get. Okay. So with this, what we are now seeing is that we have two DOS graphs here, and they're supposed to be similar according to the information in the encyclopedia, and indeed they do seem very similar, the same kind of peaks, and the similarity measure is really around the Fermi level, so it's going to be measured around this 0 line here, and it's really focusing on this area similarity, because it doesn't make sense to construct the similarity very far away from this area, which is actually typically the interesting part. So at least this validates that the similarity information that was present in the encyclopedia does really hold true, and these two materials do have a similar DOS in the end. So this really concludes kind of, I hope I've given kind of a glimpse to what is really possible with the current encyclopedia API, what kind of things you can do with it. And as I said, the examples, this whole script will be available later on the tutorial site. So you can take a look at there and try running this yourself. What I want to just say here before we finish is that we have these few interesting future prospects that for the encyclopedia that we are building right now. I'm just going to go into presentation mode. So the future for the encyclopedia. So we here at the very end, I want to discuss some of these developments that we are after for the encyclopedia. So, and one of these is this improved material detection that will address this issue that we also saw in the GUI example, so that there are these interesting calculations and interesting experiments done on highly complex materials, which highly complex systems that consist of multiple materials. And so far, what we've seen in the encyclopedia, it's all about these single materials. So it's either bulk material, a 2D molecule, or 2D structure, or a polymer. But then there are these, for example, in what I'm showing here is a kind of a heterostructure, where the structure is periodic in these basically X and Y directions, and then it has like a stacking in the Z direction, and it's stacked from several different materials essentially. And now we are building this kind of a system that allows us to separate these different parts using this kind of a periodicity-based clustering, so that we can detect the individual materials from here, and then hopefully provide links then to the encyclopedia. So what the process would look like is that if you have a calculation which has a very complicated structure, it will still be processed normally, but inside the results that we give out, we're going to tell you that, okay, this entry consists of, it has this material with this ID here, this part, and another material at this middle part, and then the third material here at the very bottom. So with this, we hope that we kind of provide this, first of all, better processing for these samples, and then better findability, because it's really difficult to find these kind of interesting structures unless you are able to say something about from which material they are constructed from. Because just, for example, typing the elements would get you really confused, because this has like a bunch of elements that don't really tell you anything unless you know the partition. And what this will look like in the end is that for these complex entries, we're gonna display this kind of a, and now we're talking about the repository. So in the repository, when you have an entry, a single calculation, we're gonna display this kind of a topological tree, which has these partitions like spelled out for you, saying that there's the original system, but then also that there is a subsystem, which can be highlighted like this, for example. And then this subsystem can also, we have this information that it consists of this, it's built from a material which has this kind of a conventional cell. And this is where we get back to the encyclopedia. So we can provide the material IDs for these conventional cells here. And you have this link now going from this entry to material in the encyclopedia. So this way we can, first of all, just create these links, which is important, but then also enable these kind of searches where it can say, I want to find all kinds of calculations that contain some part that has this material ID. So it doesn't have to be this bulk material itself. It can just be this kind of very complicated thing that has a part that is consisted from this bulk material. So this way we hope we can create much more meaningful queries, and also kind of, as Christoph also mentioned, to some at least to some degree, tackle these complex things that are really the interesting parts. When we talk about devices and applications, you're typically talking about structures that have a lot of different components, like a solar cell or something like this. So you need to be able to search for these individual components, and this allows quite nicely to automatically get these in quite a bit of cases. So this is not, of course, possible for all kinds of things, but for example, for these heterostructures, it is possible, and we are currently developing this kind of feature. And another thing that I also kind of briefly mentioned is that we are building this tighter integration between the repository and the encyclopedia. So currently these are kind of handled as separate services, and we are trying to bring them more closer together, so we can consolidate the look and feel really of these NOMAD services, and also simplify our technology stack basically. So hopefully in the future we're going to have a much tighter integration, where possibly that you'll find the encyclopedia in the same kind of platform that we use for the entries, and we can offer these kind of more complex queries also for the materials that are not currently available in the encyclopedia. So these are just like two of the highlights that I wanted to mention regarding the future of the encyclopedia. And I think basically with these two steps, we will have quite a well integrated package where people can choose based on their interest, whether they're interested in individual entries, or they're interested in data sets, or they're interested in materials. So we could find these search interfaces in the same place and really kind of consolidate our platform a bit more. Basically, this now concludes what I had to say. And now there's still opportunity for you to ask more questions about the API, about these future prospects that I mentioned, or anything else you want to mention. So the floor is yours once again. Just raise your hand or type in the chat, or just shout out if you have any questions.
Yeah, thank you very much, Lauri. I don't have a question. I just want to encourage others to ask questions.
No. And we then also have tomorrow the Q&A sessions, targeting different time zones. You can find the details in the tutorial website. So there you can also, if you want to play out more with these examples and you have more questions, then I'll be there to also answer any possible questions that you might have. So yeah, Hampus, go ahead.
Yeah, so is there a way to deal with, I haven't really looked around too much, but like with solid solutions, so say that you have like some material and then you have like a continuous, substitution between two elements, and then is there some support natively for this, like to say that you have a range then of compositions there and you look at for values within this range, or?
Not really. We haven't thought about that too much. I guess it could be to some degree possible. What would be like a typical example that you would envision that has this kind of?
So, for example, there's a lot of research now on these perovskites, or I mean, we can take something even similar, like it's more simpler, like 3-5 semiconductors, right? You typically exchange two of the elements, and then you tune some properties, right? So there's a lot of properties that depend on, because the crystal or the cell parameters change and the overlap changes and things like this. So typically a lot of things depend on the exact or the ratio between two elements which are in the solid solution, because this tunes the size.
Okay.
And then I'm not really sure how this is with this hash, how this works, like, because it wouldn't really make sense to create a hash for every single resolution. Like if you have 33.4 or 33.5, like it's more like you would want to say that, okay, I treat everything that is like, I want it with, I don't know, 5% resolution or something like this. Look at results for this.
I think these kind of really kind of structures that where you cannot really assign a single material, they're really, as you said, very tricky, and I cannot at the top of my head say how you would deal with them in terms of searching, for example, as you said. I think it's an interesting question. I
think you would have to, like, sort of, I mean, just from the top of my head, you would have to somehow say that, okay, we give an ID to something which is a solid solution with these two components, and that is given one ID, and then with some key that it is a solid solution, and then you would have to have an additional parameter which would be you would typically call it X if you have a single variation, which is just the ratio of the two. And then you would have to additionally specify this. So I think you would have to treat it like separately.
Yeah. So once again, I think it becomes this case where the automation that we have built cannot really do this for you. So it becomes your responsibility, kind of, to specify this. But if you specify this and you we could define this, for example, this kind of percentages, the ranges in there. Yeah, I could imagine that it would be possible, but then yeah, it requires a manual intervention. Like I would expect that almost anything coming from experiments will require some degree of this, because unless you have a really well characterized structure, you typically don't have the atomic positions and elements and the cell there really.
Because for a calculation, you would just have a very large unit cell, right? Where you have then a fixed ratio of elements, and these would show up then as different calculations. Like they would show up as different elements in the encyclopedia. Okay, yeah. Mm-hmm. Okay, thanks.
Yeah. I think
Does anybody else have any question? I don't see it.
Yeah.
So thank you very much again, Lauri. That was a very comprehensive, at least in my opinion, tutorial. Thank you very much.